Okay, right? So,
Hello everyone. So welcome for the Institute Colloquium, and today it's a pleasure to have Professor Amaresh Jaiswal with us. So Amaresh is a associate professor at NICER, Bhubaneswar, and Amaresh did his PhD from TIFR. He in his PhD work he has done some fundamental contributions in understanding or deriving third order hydrodynamic equations from kinetic theory, and his work was of fundamental importance, so he got the Best Thesis Award in TIFR. After that, he went to GSI Darmstadt for his postdoc, and then after his postdoc, he was faculty member at NICER since 2017. So Amresh works on areas in different areas in hydrodynamics, kinetic theory, and more importantly, to understand how these kind of theories can be applied to understand the intricacies of the heavy ion collisions. Now, of course, he has also some applications of it in graphene and lower dimensional systems, and he will tell us more about all of these in this talk. So, please, Amrish.
okay. Thank you, Shantanda, for the kind introduction. Okay. All right. So, I will discuss about our recent work on formulation of relativistic hydrodynamics with explicit angular momentum conservation, which we call relativistic spin hydrodynamics, and then generalizing it with also magnetic field, okay, and its applications in heavy ion collision as well as alternate systems. So, let's start with one very interesting phenomena observed in solids, where a ferromagnetic material, when we put it in external magnetic field, okay. So ferromagnetic materials have electrons, which are spin half particles, charged particles. So basically, each of them are a magnetic dipole. So they align in the presence of magnetic field. So in that case, the alignment of magnetic dipole also leads to alignment of the spin of the electrons, and therefore there is a unbalanced angular momentum due to spin of the electrons being aligned, which leads to the rotation of the ferromagnetic material in the opposite direction. So the idea is that if you apply a magnetic field, the ferromagnetic material rotates. Okay, this is the Einstein-de Haas effect. It's converse. So if you apply magnetic field, the material rotates. So if you spin the material, will it create magnetic field? That question is also yes. It's not. That's the converse of the Einstein-de Haas effect, which is known as the Barnett effect, which essentially leads to spontaneous magnetization on rotation. Okay, and that magnetization again is basically leads because it's the same ferromagnetic material, so it will again lead to alignment of particle spin. So it leads to magnetization as well as spin polarization of electrons in the ferromagnetic material on rotation. Okay, so these two effects let's keep in mind when we go to the formulation of relativistic hydrodynamics. So why do I worry about relativistic hydrodynamics? One of the systems is the quark gluon plasma formed in heavy ion collision, which has a the major part of the evolution is governed by relativistic viscous hydrodynamics. Okay, we need dissipation to explain certain flow phenomena and so on. But the idea is that relativistic hydrodynamics is applicable in heavy ion collision. Okay, so as a high energy physicist, I am interested in formulating relativistic hydrodynamics, for the system appropriately. Okay. So in heavy ion collision, okay. So heavy ion collisions are two heavy ions with all the electrons stripped. So they are basically charged, positively charged particles moving towards each other with very high speed. So if there is a finite impact parameter between the colliding nuclei, so there is essentially a very huge current, because they are moving very relativistically. Okay, so there is huge current, okay, whose centers are not aligned. So they, at the point of impact, they create a magnetic field, a very strong magnetic field of the order of 10 to the 14 Tesla, which is of course very transient, but very, very high. Okay, so that's one feature that we should keep in mind. So this magnetic field decays very fast, at the speed of light actually. As the spectators which are traveling at the speed of light, they move apart, the magnetic field also decays. But nevertheless, it's there. It's in the early stages. Okay, and it decays quite fast, as you can see, the magnetic field. It depends whether the QGP formed. Okay, so when we try to model it, whether it's a non-conductive or a conductive QGP. So it depends on the conductivity of the QGP, and therefore, if there is a finite conductivity, then the field sustains for a larger time. Okay, but it decays. Okay, and it's usually measured in units of m pi square. Then, because of the same feature that there is a finite impact parameter which leads to magnetic field, that it also leads to an unbalanced angular momentum in the colliding nuclei. So because there is impact parameter, so the overlap zone so there is a the collision leads to an unbalanced angular momentum in the overlap zone, which is pointing along the y direction. If we assume the collision to be happening along z and the impact parameter to be along x, then the angular momentum as well as the magnetic field points along the y direction. Okay. Which one? Sorry, this one. This plot or this plot you mean? This is simply retarded magnetic field. You can just, because of the fact that charged particles are colliding, so this is very easy to generate, this plot. Okay, these are not experimental; these are just theory model calculations. Okay, and similarly, these are also model calculations where you can assume the nuclei to be hard spheres, or distribution is given by Woods-Saxion distribution. So you see that the angular momentum as a function of impact parameter. Of course, if the impact parameter is 0, then you don't have unbalanced angular momentum left, because there is no unbalanced angular momentum to begin with. But when you keep on increasing the impact, the angular momentum increases, but it decreases because the effective, because the fireball volume becomes smaller and smaller, and the effective moment of inertia gets kind of decreases. So the angular momentum left in the, because if you go far apart, then there is no collision, and then there is no angular momentum in the, there is no medium, so there is no angular momentum. So that's what we expect. There is a sweet spot for the impact parameter where we expect to have a large angular momentum. So what do we learn? So we have, okay, yes. Well, I mean, so why is it not symmetric is what you're asking. Okay, so that is, I mean, in general we don't expect it to be symmetric is what I would answer, because anyway these are the model calculations. So I don't see a reason why it should be symmetric. I mean, this distribution is simply, there is not, I would not associate distribution to this curve. This is just a model calculation with Woods-Saxion or hard sphere. But a priori I would also expect it to be symmetric as a function of B, as a function of impact parameter, because of the fact that if the impact parameter is 0, it has to go to 0. Okay, and the Woods-Saxion distribution, for example, has a long tail, so you have to really go very far away for impact parameter for the angular momentum to become 0. So I don't expect it to be symmetric anyway. Okay. All right. So these features were observed. So the fact that there is angular momentum being deposited. Okay, and the consequence of that was measured. So I will tell you how we measure this. What we really measure to claim that we have seen deposition of angular momentum in heavy ion collision and so on. Okay. But the thing to notice is that we agree that there is a viscous hydrodynamic phase, and there is angular momentum, and there is magnetic field. So we should be worried about having the hydrodynamic equation which is compatible with all these phenomena. So that's what basically I worry about. Okay. So so let's start with what is this polarization that has been measured. Okay. How do we measure that, and what do we really claim that that a polarization, finite polarization has been measured? So let's look at the decay of a scalar particle. Okay. So a scalar particle is basically in the rest frame of the particle. Basically, it's just a sphere. There is no feature of this scalar particle in the rest frame which breaks the isotropy. Okay. So the decay daughters will simply in the rest frame will simply go back to back, but that back to back direction could be in any direction. Okay. To conserve momentum, it just goes back to back. Okay. The decay daughters. Okay. So no anisotropy in the rest frame. If you look at the decay of many scalar particles, then you will see isotropic decay daughters. Okay. However, if you have particles with spin, okay, then the isotropy is broken by the fact that there is a direction of the spin. Okay. So if it decays, then there is a preferential direction for the decay daughters to be emitted. It's very similar to, for example, if we have so spin cannot be really classicalized, but if imagine something which is spinning, breaks apart, then it has more tendency to throw the debris in the equatorial plane because it's spinning. So, but spin is not really a classical thing, but something similar to that. That's what we should keep in mind. So, there is a preferential direction for the decay daughter to be emitted in case of particle with spin. Okay, and that forms the basis of our polarization observation. However, even if the particles are with spin, okay, but there are many particles which decay. That's what we observe in heavy ion collision. Okay, so the spins could be aligned randomly, and then you still see isotropic decay. Yeah, because the spins are aligned randomly. But this is the feature which we actually observe. The spins are aligned. Okay, not randomly oriented. Okay, and the decay of such spin aligned system would be anisotropic. Okay, and that's what has been measured, and that's what so this has been measured for for baryons, for mesons. Okay, and also two different type of feature, global and local polarization. I will discuss both of them, what they are. Okay, but this is kind of new thing which came up. These measurements are pretty recent. Well, 10 years, give or take, which is kind of a recent phenomenon, and it's a different type of collectivity. So by collectivity in heavy ion collision we mean flow, for example, or for example, PT spectra also has a thermal nature. So these are collective features, but then this is also a collective phenomena. The alignment of spin is a collective phenomena which we see in polarization measurements. Okay. So this is this P, the percentage polarization that that is plotted on the y-axis as a function of collision energy. Okay. So you see that this is polarization along the y-axis essentially. Okay. So because the angular momentum which we discussed was along the y-axis, so this is measured along the y-axis as a function of root s. Okay. And then there are lambda and anti-lambda particles, and you see that there is a general trend of decreasing trend as a function of root s, and this decreasing trend is because as you go higher and higher in energy, okay, then in the longitudinal along the longitudinal axis, the fireball is more and more, we have this Bjorken boost invariance. It's more and more symmetric as a function of z. It becomes boost invariant. Okay, and that symmetry is what leads to lesser deposition of. It's like what is also known as transparency of the nuclear colliding nuclei. Okay, in lower energy there is a kind of baryon stopping, which actually leads to the nucleus rotating. Although the colliding energy is small, but the angular momentum being deposited at low energy is larger compared to the baryon, this transparency of the medium in very high energy. So although the energy is large, but the transparency doesn't lead to much baryon deposition. So therefore, it decreases root s. What we do see, and these are, of course, these are old results, but there was a hint of lambda and anti-lambda, okay, having different polarization values, which could be attributed to magnetic field playing a role in differentially leading differential polarization measurements. Of course, you can argue that both of them are some lambda is uncharged, okay, but actually the polarization is mostly governed by the strange quark content of the lambda, and that because the strange is paired with up and down, okay. So the heaviest quark is the one which actually controls the because the spin flips for the lighter ones, it's easy to flip the spin compared to the heavier quark. So the polarization is governed by the strange quarks, and then and the charge of strange quarks are different in lambda and lambda, and therefore one should look at the magnetic field also in the calculation. All right. So in the heavy ion collision, basically we have there was a hint of maybe magnetic field playing a role. Okay, angular momentum will act in the same direction for both lambda and anti-lambda. It doesn't care about the charge. Okay, it just cares about the mass or the so-called moment of inertia. Okay, yes.
Like some form of asymmetry variable which is computing. What is p bar h?
Yeah, so this is polarization measured along the y-axis in percentage. Okay, so
it decreases very drastically from root s
yes,
9 to.
as a function of collision energy, it decreases because at lower energy there is this feature of baryon stopping. The colliding nuclei almost stop. Okay, and at higher energy they simply transparently pass through each other. So there is more deposition of angular momentum at lower energies compared to that at high energy. Okay, and hence this is what, so we see that, forget about these, but at least we see a decreasing trend at very high energy. Okay, so when you increase energy, the polarization decreases. So this is the reason. But the idea was that there is also the difference between lambda and anti-lambda, and why was that? So there is a hint of magnetic field playing a role, and angular momentum, and viscous hydrodynamics. So we should worry about relativistic hydrodynamics with angular momentum conservation. Okay, so let's first discuss relativistic hydrodynamics. Quickly, I will outline what is this relativistic hydrodynamics. So that too in an intuitive setup, which is kinetic theory, which also I find comfortable to work with. So we have this relativistic dispersion relation for energy and momentum, which is the only kind of relativistic input that goes into the whole formulation. Okay, we deal with distribution function, which tells us that what is the number of particles, okay, in a phase space volume element located at x and p. Okay, and and we work with statistical assumptions that this this volume element delta 3x, which is located at p, okay, is large enough such that the number of particles in this small volume element is this, which we call the fluid element, is large, so that you can make a statistical average, define a temperature, and so on. Okay, however, it is small enough compared to the total volume of the fluid. Okay, so that you can consider it still as a fluid element. Okay, so this is the separation of scales we need. Okay. Right. So what one can do is, using this distribution function, one can define the particle current. Okay, so we simply, the particle number is simply integrating over the momentum. This is the number density, because if we integrate over the momentum and the d3x and d3p, that should give the total number. So this is the density. This is the current density, particle current density, and these two can be combined in a unified way, where d3p by p0 is Lorentz invariant, and we have this particle 4 current. Okay, yes. And similarly, what we can do is we can define the energy density, where we weigh the distribution function with energy and integrate to the energy density. Okay, and then we can have energy flow. So energy weighted with the velocity is energy flow. Momentum density is simply weighted, the distribution function weighted with the momentum, and then there is a momentum flow. Okay, and all these can be combined together with this definition of the velocity to write the energy momentum tensor of the fluid in terms of distribution function. All this is relativistic because d3p by p0 is Lorentz invariant scalar. Okay, so what do we how do we see that the conservation of particle number or energy momentum? What is the corresponding equation? So this total number is simply, we take the number density, integrate over the volume, is the total number. Okay, and this could be net number, for instance. So for example, So relativistically, there could be particle production annihilation processes. Okay, and then the total number is not a conserved quantity. But what is conserved is net number, particle minus antiparticle. The number what you start with, that should be conserved. This could as well be net number. And so the point is that some property of the number should be conserved. So d dt of n as a function of this n should be a constant in time. So what one can do is one can simply apply del del t, and this is a surface term we can add because we are integrating over d3x. This is a surface term which we can add, and essentially the idea is that with that we get the conservation of forecurrent. Okay. Similarly, we can define the particle, the total fluid for energy momentum. Okay, which is just you take the momentum density, integrate over the volume, and the total energy momentum conservation leads to this. Okay, these are. I'm sorry if I'm going more lecture-like, but just to get this out of the way, because the conservation equations look like this. Why it looks like that, I wanted to be clear. Okay. So then, what more is how do we, write down the expressions of these particle forecurrent and energy momentum tensor in equilibrium? Okay. So the equilibrium distribution function we are familiar with is of this form, where R can be 0 plus or minus 1 for Fermi-Dirac, so 0 for Maxwell-Boltzmann, plus 1 or minus 1 for Fermi-Dirac and Bose-Einstein. Okay. So but this is not in a Lorentz invariant form, because there is a E which is P0 component. Okay. So to make it Lorentz invariant, we introduce a U, a four velocity kind of thing, such that when U takes this form in the rest frame of the of the system, whatever you are considering, okay, you recover the known form of the distribution function. Okay, so U has to be of this form to recover the known form of the of the distribution function, equilibrium distribution function. Therefore, we must have U mu to be normalized to 1. That is one condition. Similarly, what we can do is let's count the degrees of freedom that we have left from the equilibrium distribution function. Okay. So remember, momentum is integrated over to generate the hydrodynamic quantities. So we are left with T and mu. So beta is 1 by T, alpha is mu by T. Okay. So T and mu are the two scalars in the system. U mu is the one vector, and G mu is one tensor because we have U dot P, which needs G mu to be defined. So these are the degrees of freedom we have. Okay, and the most general construction that we can do in terms of these degrees of freedom for n mu, the particle current, and the energy momentum tensor is this here. This is the most general construction we can do, keeping in mind that T mu nu is symmetric in mu and nu. Okay. Then we have to determine these coefficients C1, C2, and C3, which is function of T and mu. So one more thing, there are three coefficients C1, C2, and C3, function of T and mu. Okay, so they must be related by a relation 3 as a function of 2 variables, and that is the equation of state. That is what. Okay. So these three related by T mu is the equation of state, and then to determine the coefficient C1, C2, C3, we go to the rest frame, where the particle forecurrent is only density, and energy momentum tensor takes this form, which is the Pascal's law, that pressure of the fluid is equal and opposite at each point. The zeroth component is energy density. And when we compare that with the structure that we wrote down, the most general structure, we can determine C1, C2, C3. So this is the form of the particle forecurrent and energy momentum tensor. So just the form of the equilibrium distribution function is enough to write down this tensor structure, and we must keep in mind that epsilon p and n are related by one relation, which is the equation of state. So this is the usual energy momentum conservation. Now angular momentum conservation for fluids. But to see that, let's start with angular momentum conservation for particles. Okay. So angular momentum we can define as x cross p for a particle, and in terms of tensor components, we can write it in this form. Okay. And this we also have the angular momentum conserved. And basically the structure also leads to this form of the equation. Okay. what you can do is we can simply generalize this relativistically. So ij goes to mu nu, and it's a very easy thing to do. One can generalize this with this equation being satisfied. This is valid for point particles, relativistic point particles. Okay. What about continuous medium, fluid? Okay. So for generalize for fluids, what we do is we take the momentum of the particle, point particle, and generalize it to fluid, which is the generalized fluid momentum, the energy momentum tensor. So this L takes this form. Okay. So the point particle gets generalized to continuous medium. The momentum gets replaced by energy momentum tensor. This is the orbital part of the angular momentum. Okay. And the divergence of this is antisymmetric part of T mu nu, and remember T mu nu which we wrote down from kinetic theory was symmetric. So this orbital part is conserved, and this is one of the main reasons why people didn't worry about angular momentum conservation till very recently, because it's automatically conserved if energy momentum tensor is symmetric. Okay. So then it doesn't give a new equation to solve for, it's an identity. Okay. But what about if you have particles with intrinsic spin, which we bothered about in the previous slides, that if you have particles with spins, they can align, they can have a collective behavior. So how do we understand that? So if we have particles with intrinsic spin, okay, the total angular momentum has orbital part plus the spin parts getting aligned. Okay. And the total angular momentum conservation is what we should be worried about. Okay. And that is not simply conserved, that is not an identity. Okay, because we have a new structure here. Okay. And this is what forms the basis for spin hydrodynamics. Okay. So we have the total angular momentum, and the total angular momentum conserved along with conservation of energy momentum tensor leads to these two equations. Okay. So energy momentum tensor is conserved, and spin tensor divergence is equal to the antisymmetric part of T mu nu, which is 0 if we have a classical, let's say, energy momentum tensor which is symmetric in T mu nu. So spin tensor also seems to be conserved. However, energy momentum tensor need not be symmetric always. Okay. So for example, if you remember when we do electrodynamics, we simply take the Maxwell, this Lagrangian for electromagnetic field, and when we use Noether's theorem to calculate energy momentum tensor, it turns out to be the first thing that we get is a energy momentum tensor which is not symmetric, and we symmetrize it using a Bell-Infante construction. Okay. So there is some kind of freedom in choosing T mu nu to be symmetric or not. In a more generalized setting, this is what the freedom is. So what it means is that there are essentially these are mechanical forms of energy momentum, the energy momentum as well as the angular momentum. Okay. So you can shuffle the contribution between them. Okay. And still these two equations can be satisfied even with the tilde quantities, and we have there is a freedom of phi tensor. Okay. So there is a extra degree of freedom which pops out. Okay. And that has to do with the fundamental symmetry of space time. So essentially the idea is that this phi could be in a non-trivial space time structure. You can actually relate it with the torsion of the metric. Okay. But if that is not there, then we have this symmetry which is so we don't have torsion in the metric. I mean, at least in the Einstein gravity we don't have that. So we cannot really fix this up. Okay. So there is a freedom. All right. And it leads to certain problems with because if I cannot uniquely define my energy momentum tensor and spin tensor, then I cannot uniquely define my transport in the system. For example, shear viscosity, bulk viscosity. Okay, viscosities are well defined, but transport in connection with the spin diffusion, those becomes a little tricky. Okay. So
But what happens due to these additional terms for the energy density? This doesn't affect us.
this one here,
Yeah.
actually no, because
So 0, 0 component has some properties.
so mu nu is antisymmetric. Okay. So and you have to contract with u mu nu to get the energy moment contribution to energy density, so that vanishes. Because
Similarly for pressure also.
similarly for pressure. So
So it will only show in the pointing vector all this off
Yes.
diagonal term.
yes, the off diagonal term. So that is and the antisymmetric part will, so antisymmetric part of T mu nu will carry information about the spin tensor. So that's basically the angular momentum of this medium. Okay, so that is somehow it leads to certain new transport like rotational viscosity, boost heat conductivity, the kind of new transport in T mu nu. Okay. However, what you can do is you can keep on shuffling, and this will change. So it leads to a real problem in counting of how many transport coefficients we have in connection with spin degrees of freedom, and that is still an unsettled
But
issue.
in electrodynamics with spin,
Yes.
do you have additional contributions to Poynting vector because of this?
So actually,
A radiation reaction or something like that?
so I haven't done one work with gauge fields. So I have been working with spin half particles. So I mean the only thing that I have read about the gauge field is this Bellin-Fante construction. So basically we use the other current to construct this, and then we can actually get rid of the whole angular momentum part itself, right? We can simply set it to equal to 0, and then T mu nu becomes symmetric. So, but I have not really, okay, I'm not sure about this Poynting vector. So we have been working with spin half particles. Okay, so essentially this is how we do. We work. So this is how the equilibrium distribution gets generalized for spin half particle in presence of angular momentum. I mean spin. So there is a +1. Okay. So I like to point out that we get an extra contribution to spin due to spin. Okay. That is this omega dot s. The double dot is omega mu nu s mu nu essentially. Okay. And +1. Okay. +1 is because of the statistics of fermions. Okay. This is simply Pauli blocking factor. Okay. And this is the fact that we have generalized the phase space. So the phase space now gets extended by the spin also. Okay. So this is the extension of the phase space, and this is just the statistics of the fermions. Okay. So the +1 doesn't take care of all aspects of spin, by the way. That's what I am trying to drive at. Okay. So and how do we understand this extra term? So omega mu nu. So S is the spin tensor of the particles. Okay. The S, for example, for fermions, it will be commutator of gamma mu gamma nu. Okay. I will come to that also later on. But this is and then the omega is the Lagrange multiplier, which essentially is, for example, in beta and alpha are the Lagrange multipliers corresponding to energy momentum and current conservation there, and similarly omega is the Lagrange multiplier corresponding to the angular momentum conservation. Okay. And this is of course a classic. This we have done we have written in when we treat spin classically. What do we mean by classical treatment of spin? So the idea is that we want to go out of equilibrium. So there are very few ways of going out of equilibrium. One such is that I am aware of is the Boltzmann equation. Okay, and for that I have to have a classical phase space. Okay, so somehow I have to really classicalize the spin half. So how do we do this? What we do is we take this so-called block sphere. Okay, where the only two spin states that are allowed quantum mechanically are this plus half and minus half. Okay, but what we do is we say that okay, all the points on this block sphere is allowed, subject to the constraint that if I integrate over this spin vector on the block sphere, okay, then I get 2. 2 is just counting the two spin states. So plus half or minus half, there are two spin states. That is this 2, and the radius of the block sphere is given by this, this factor half into s into s plus 1. Okay, so this is like kind of classicalizing the spin. Okay, we only keep the essential features of the quantum nature, which is the fact that s into s plus 1 should be the length of the radius of the block sphere, and 2 should be the total number of spin states when we integrate over the spin states. Okay, so in this way it becomes easy to, so now things become continuous. You can simply extend the phase space. Okay, and write down in terms of this phase space xps dependent distribution function, we can write down the conserved quantities. Okay, and the equation of motion are these three equations, because T mu nu is symmetric, therefore spin tensor is also conserved. Okay, and then one can go out of equilibrium. So once we have this phase space extended distribution function, we can go out of equilibrium using the Boltzmann equation. And then we have dissipative hydrodynamics also, spin hydrodynamics also constructed from using the correction out of equilibrium that we can calculate using the Boltzmann equation. In some approximations we can do that, and we can generalize spin hydro to dissipative spin hydro. And these are the dissipative phenomena which we are aware of. Shear, which is resistance to change of shape, to change of volume is the bulk viscosity, and then there is conductivity, okay, resistance through flow of charge and heat. But the dissipation to spin is something new and which we have to really understand. So there are Kubo formalism which are required, because what we do is when we try to understand, at least when we try to construct expressions for transport coefficients using this Zubarev's approach, Kubo formalism, what one does is one has to project out all different components of the dissipation, and that leads to a intuitive understanding. That clear understanding we don't have yet, okay, about the spin, dissipation to spin part. And what one can, so this is the magnetohydrodynamics part. So what we can do is we can also include the contribution due to the electromagnetic field in the picture. So we have the fluid part, the field part, and the fluid field interaction, which is a non-dissipative kind of interaction. This is like magnetization or polarization. So it is not really a dissipative interaction, okay. So there are these terms which one can write down, and the only interesting thing that happens in this picture is that the field can carry force and also point like pure torque. So this is like so for imagine you have a pencil which you keep up in your palm and then rotate. So at the tip of the pencil is a pure torque. There is no force but just torque, okay. So that kind of feature is carried by field, okay. The electromagnetic field can carry such components, and then one has to worry about this pure torque also, so which we have not done in this paper, by the way. So we set it equal to 0 and then we derive, okay. So the torque is just moment of the force, is what we consider, okay. And so in that case, if we don't have the pure torque, the spin tensor is conserved. And so the idea is that these equations which we have from the consideration of field, one can simply take that also from from the moments of the Boltzmann equation. We get the same equation, and then basically we can derive the expressions. This is something interesting. So what we can do is we can calculate the magnetization of the medium, okay. That is just we integrate over the magnetic moments of the particles with its corresponding distribution, okay. So particles minus antiparticles, and in equilibrium we have this structure, and the magnetic moment for a point like particle is proportional to its spin with a gyromagnetic ratio, okay. So if we put this and we integrate over the magnetic dipole moment of each particle, okay, we get this equation up to linear order in omega, okay. So what we observe here is that the magnetization is proportional to omega mu nu, the spin tensor, that this Lagrange multiplier which we had for conservation of spin, okay, and they are linearly related, okay. So and omega mu nu, this corresponds to rotation of the fluid, okay. So the rotation of the fluid leads to magnetization and vice versa. That's what is Einstein-Diason Barnett effect, which we, so if you remember the first two phenomena that we discussed. So rotation produces magnetic field, or magnetic field produces rotation, okay. These are Einstein-Diason Barnett effect, which we which we get in our formalism, okay. That was spin hydro. Now spin magnetohydro, okay. Now let's go back to some applications. So we have to really apply it to certain physical systems. So in heavy ion collision we have this, I showed this earlier, okay. So so if I compare the data with theoretical results for the y component of the polarization, which is along the angular momentum which is deposited in the fireball, okay, then all the theory calculations you see matches within error bars with the observation, okay. Almost all the theory calculations, okay. This theory calculations uses something called thermal vorticity. I will discuss what that is, okay, later on. But the point is that all theory calculations which uses this particular component of spin hydrodynamics, okay, agrees with this result for global global polarization, which is the angular momentum, which is along the angular momentum y component of the angular momentum basically. Now there is another measurement which is along the z component, so which is along the beam axis. Okay, so that is called local. Okay, this local polarization, there is a sign problem. What I mean by that is that the same feature which we use to calculate the global polarization, if we use that, we calculate something like this. This is a theory calculation where, so this px py in px py plane. Okay, basically as a function of angle in the azimuthal angle in the momentum space, you see in the first quadrant there is it's negative, then positive, then negative, then positive. This is what we calculate. What we measure is the opposite. So in the first quadrant it is positive. This is the measurement. Okay, so the measurement is exactly opposite to the theoretical calculation. Okay, the same calculation which actually agrees with global polarization doesn't agree with the local polarization. Okay, and when one looks at it from a naive perspective, so in the transverse plane there is the elliptic flow. The elliptic flow is generated. So you look at this first quadrant, there is elliptic flow, which is, if you look at the general nature, there is the rotation is kind of this way. This is like this, and similarly in the other quadrant. So this should be positive coming out in here, negative, positive, negative. Okay, this is what we expect from general considerations of flow, elliptic flow. But if I use the thermal, what is this? This is the prediction of spin hydrodynamics, which is used to calculate polarization. If I use that, I get the opposite in calculation. Okay, so the regular flow doesn't align with the thermal vorticity. Okay, so that's a problem. This is called the this sign problem. It's not the same QCD sign problem, but we like to emphasize the problem. Let's say so. It's called the sign problem in longitudinal component of the polarization, and there are several reasons. One of the main reason which I suspect, and not just me, but many of us suspect, that the fact that in the local polarization, the assumption of thermal vorticity itself may be wrong. I mean, the thermal vorticity itself may be wrong, and why is that? Because the thermal vorticity is a solution, is a global equilibrium solution actually. It's not a local, it's a global equilibrium solution. Okay, and the fireball is too short-lived to achieve global equilibrium. Okay, so let me just discuss quickly why it is a global equilibrium solution, why the orbital this thermal vorticity. So the angular momentum operator one can write in this way, which we already saw. Okay, and what one can do is using this angular momentum expression as well as what we have for energy momentum and particle current, we can calculate the local equilibrium density operator by minimizing the entropy. Okay, and that local equilibrium, this density operator has this form. Okay, if I say that this, so using this density operator, I can also calculate the total angular momentum, conserved angular momentum in the system. Okay, and if I want this to calculate the global angular momentum, okay, the condition for global equilibrium, then this must be independent of the choice of this hypersurface sigma over which I am integrating to find the angular momentum. Okay, so that leads to these conditions. So these conditions are for global equilibrium. Okay, so what we see here, the thermal vorticity turns out to be a condition of the global equilibrium. Okay, and the fireball is too short-lived to have achieved global equilibrium. That's the problem. So then that's why this fails for local polarization. Okay, so can we look for an alternate system where this issue of short lifetimes may not, we need not worry about short lifetimes. Okay,
But why does spin take so much time to thermalize? Because other degrees of freedom may have thermalized.
But even other degrees of freedom come to a local equilibrium, not global equilibrium. Global equilibrium you have to really wait for, because that is even not achieved even in.
But when people talk about the particle detection
production
using
and
the thermal model,
yes,
that is a global equilibration.
that's a bad assumption anyway. Thermal model, you know, there is this thermal model or statistical
That is
hydrodynamics
what
model.
people use in the experiments.
Yes, but one should actually the most, I mean, state of the art is one should use hydro model, okay, and that is a local equilibrium feature. So even, but anyway, spin-spin interaction, okay. So there are certain estimates, there are many papers which says that the spin-spin interaction, I mean the time scale for it to achieve equilibrium is large, okay. So the mean, one can just simply relate the mean free paths, so-called mean free paths for the spin-spin interaction, and that is large actually, okay. So that, so therefore, yeah, so therefore what, I mean, one should look for an alternate system where we can test the prediction of spin hydrodynamics, which is the thermal vorticity, and which does not suffer from this short lifetime problem. Yeah. So one such system is graphene. It's a tabletop thing. Okay. So it's not a transient system which simply has finite level. We can just wait for as long as we want for the system to achieve global equilibrium. Okay. And graphene has an interesting thing. So it has a honeycomb lattice and it exhibits this relativistic dispersion near Dirac point. Okay. Why I call this relativistic, because the energy and momentum are linearly related, and with the coefficient being Vf, the Fermi velocity, not c. But nevertheless, this is more or less what we require for us to construct relativistic kinetic theory and calculate the relevant required degrees of freedom, okay, for graphene, and assume that there is, I mean, we can simply wait for it to achieve global equilibrium. That's not a problem at all. Okay. So one can use this. So this time, since I am not planning to go out of equilibrium, what we can do is we can define the spin tensor, and instead of integrating over the spin degree of freedom, instead of classicalizing it, we can simply sum over the trace, take the trace over the gamma matrices. Okay, and basically one gets the same structure of the spin tensor and energy momentum tensor and particle force-current. Okay, and what one can do is with this form of fluid velocity and the structure of temperature and chemical potential. Okay, one obtains omega mu nu. Okay, this is the thermal vorticity, which is a solution of the, so which is also obtained from the solution of energy momentum tensor conservation, spin conservation, and particle force-current conservation. Okay, so basically these are consistent with the hydrodynamic equations as well. Okay, so this we expect because we found that from this density matrix approach also we see that this the global equilibrium should be defined for this thermal vorticity, and we do find that also it solves the hydro equations as well. Okay, so we can go ahead and calculate the magnetization.
And what do you precisely mean by this chemical potential?
This is this simply measures the difference between particle and antiparticle. In the context of graphene, is it what you?
Yeah.
Okay.
Is the
This
gate
particle
voltage.
hole. So
The
electrons
gate
and holes.
voltage. You
Which
regulate the gate voltage, and then I guess you can change the Fermi surface some way.
Yes.
and then-
So that is this view. Yeah. So that is one can simply change. Usually near Dirac point there is almost charge neutrality. So that is
the mu is 0.
mu is almost 0. But
Yeah, if you don't give an external voltage, then mu is always 0.
0. But we can always give we can tune it. We can shift that is what you said. We can shift the Fermi surface. Okay. And so what we can do is this. We can do we calculate the magnetization. Okay. And as a function of the thermal vorticity. Okay. And this is what we get with the solution of the rigid rotor global equilibrium. So the proposition is that we can, for example, this is magnetization which can be measured. Of course, there is a E sitting here, which makes it quite small to measure, but nevertheless, it's in principle measurable quantity. Okay, which points along the z-axis of the 2D plane. The magnetic field points along the z-axis. Okay, transverse to the plane. Okay, and so the idea is that we start with this. So we can actually, for example, we can provide this temperature gradient. Okay, externally. So what we want to do is we want to initialize the system such that if we leave it, then it relaxes to the global equilibrium, which is closest to thermal vorticity. Okay. So we can simply provide this gradient where gamma is takes this form. Okay. Externally, so we can, so I have been talking to the experimentalist. So what one can do is one can have these nanowire coils, okay, which through which if we pass electricity, it will lead to, it will heat up the surface, okay, and we just need to maintain this temperature gradient, and then we switch it off. When we switch it off, the system simply relaxes to the nearest equilibrium, which is this set of equations, okay, and then you measure and we can wait enough for it to relax to global equilibrium, and then finite magnetization is supposed to be measured perpendicular to the surface of the graphene. That's the proposition, and this is what I have been working on recently. And our work in this direction, we have worked on non-dissipative spin hydrodynamics formulation, dissipative and spin magneto hydrodynamics as well, with my PhD student Samampan Bhaduri, who has now graduated and is a postdoc in Krakow. And then with Saurav, I have been working on other aspects of spin hydrodynamics with also geometry in picture. One can actually, so very interestingly, what one can do is one can write down the Lagrangian for hydrodynamics with matter fields. So this is a very interesting thing. Where it's very in old books you'll find this. Okay, and essentially the idea is that there is a field which corresponds to fluid, matter field, and instead of putting what I have been talking about, torsion in the configuration space, we put torsion in the field space, internal degrees of freedom, and that is an option of fixing spin tensor, and he has been working on those topics. And on phenomenology side, I have been working with Soham to write down hydro code. So we have been trying to implement this spin hydro equations in music. So that is more or less what we have been doing. Thank you.
Thank you, Amaresh, for this very nice talk and questions.
Dissipation in spin, yeah. So in spin current essentially, right? So what we mean, the idea is that, so imagine for example you have this fluid volumes which has spin aligned, okay, and there is a difference of alignment from one volume to another volume, okay, because they may not be equally aligned in all local volumes. So how do this difference of spin alignment, how does it, what kind of transport it generates? This is how we. So in principle, yes. So the idea is that this impact parameter, it generates angular momentum, and of course one of the features is also it generates V2, the finite impact parameter. But there are two different ones. So the direct angular momentum that is left over in the system is along y-axis, the one which is directly, and then there is another angular momentum which is created due to the generation of V2 itself, which is the local one. That's what I have. So there is the global one which is along the y-axis, which is at the very initial time after the collision, that's left over in the medium, because of the finite impact parameter, where the spectator goes away and it's rotating along the y-axis. Okay, and then because of the impact parameter, the flow builds up, but that happens later on during the evolution. The V2 builds up because of the pressure gradients and so on. Okay, and that generates the local polarization. So that's along the z-axis. There you see local polarization. This one, where is it? Sorry, this one, because of the V2. Okay. Yes.
All the time, I don't really know whether there are any scalar collisions. So why is it that the incorporation of spin into hydrodynamics got so late?
Yes, because these polarization measurements are not are quite recent, I would say.
So,
Not
I see. So only if you measure polarization measurables, you will get to see the effects of spin. Or
yeah,
what.
the direct effect.
Otherwise, your proton-proton collisions will give you consistent results with whatever you consider for a scalar hydrodynamics.
I mean, heavy ion collisions. Yeah. Proton-proton.
Because, okay, for example, in LHC, they have been colliding proton-proton. They are actually spin-half particles.
Yes.
So you cannot simply avoid, means, okay, of course, there are spin of quarks or whatever partons are there. They are non-zero spin. So there should be some spin effects in whatever measurables you do.
But hydrodynamics in proton-proton collision is kind of still questionable, I would say, because
It's not applicable.
huh?
It's not
I mean,
applicable.
it's not, yeah, because we have to have a larger volume for. So in
I see.
PP collision, so basically in heavy ion collision.
Sorry, I don't know the spin of lead. What is the spin of lead?
I mean, lead is part of has protons and neutrons in it. So essentially it's many, of course, baryons colliding, but then you have to go down to the QGP, which is quarks and gluons being released. So there are quarks which are spin half particles, and one has to also worry about the gluons, spin 1, which basically you were talking about, that we should also have the gauge fields and its spin. So people are working on that aspect as well. I mean, I have been focused mostly on the spin half particles. Okay.
Actually, my concern is why it is so late. That's the only reason. So
Yeah,
it's
so-
probably
so-
because of the measurables that are accessible, or the measurables that measure the effect of spin
Yes.
is
no,
being
that
measured only very recently.
recently.
I
Yeah,
see.
that's the only
Thanks.
reason.
You were showing it was drastically decreasing, so it won't be sensitive.
Let's say it is not visible because
Here?
proton doesn't have any angular momentum deposition.
Huh.
But proton has quarks, right?
That has, but there is no this.
The
It doesn't
impact,
form a medium, as we said, as you were telling. So there is no local angular momentum deposition, and the global one is also very small because it's a point particle. So there is no question of angular momentum in that proton-proton.
so in PP collision, one has to define this impact parameter. So you have to define impact parameter and then collide. Then there is a leftward angular momentum. But in PP collision, it is too small for those minute details.
Okay, so this gold collision, they are essentially
Yes.
full nucleus. which
Because
is-
the gold is like, it will have like 7 or 6 Fermi size. So then, there will be impact. One can measure it as a function of impact parameter. I mean,
I was curious because there's an Alice measurement, so I was wondering.
no, but Alice measures lead also, right?
Lead. Okay.
Alice has lead also.
Thank you.
I had a question. So when you have this spin, you introduce the hydrodynamic formalism, and then you know that these are viscous effects.
Right.
Now you are doing it in the leading order, I think,
Yes.
because your distribution functions you're writing as leading order in spin.
Leading order in omega.
Omega. Yeah.
But that is also, I mean, it's
And-
not a bad approximation because you see the percentage, 4% is the polarization. It's a small effect. So in the limit of small polarization is what we are working with.
And where do we see the effects of viscosity in this kind of treatment?
But that is a higher order correction. I mean, that correction we have not yet. It hasn't come to the application level, I would say. Even at non-dissipative level, things are already not well understood.
Because people use relaxation time approximation. And now you are telling the spin relaxation
It's
times
different.
are much larger than the
Yeah,
viscosity.
so once it becomes different, your single relaxation time approximation doesn't work. So one has to do it separately.
Okay, I see no further questions. Then let's thank Amaresh for coming and also giving this nice talk. And I hope you visit again.
Yes, I really like MSc.